Okay, 4.6 is arithmetic sequences, and you'll also hear this. Just like what it spells. You might also hear teachers call it arithmetic, because that's certainly how it's spelled. I've heard instructors call it both things, but they are one and the same, whether it's arithmetic or it's arithmetic. A few definitions to start. Sequence. A sequence is an ordered list of numbers. It's an ordered list of numbers. And that ordered list of numbers could go from greatest to least or least to greatest. The point is they are going to be in order of some sort. They're not going to be random. You may be asked to put them in order, but we need to be in order. They need to be sequenced. So here's a sequence. 5, 10, 15, 20, 25, and I'm going to call this out here a sub n. Meaning I have this list of numbers, and I'm sure you can pick up on the pattern. 5, 10, 15, 20, 25, 30, 35, 40, and this sequence is going to go on to an infinite number of terms until I end it or decide to end it, but it could be in an infinite. With a sequence, this 5 we say is in the first position. It's the first number in our sequence. This 15, this would be in the third position. And this out here, we say is in the nth position. Could be anything. Definitely has a value. An arithmetic sequence has a common difference. Has a common difference. Let's take that same list of numbers. And that could just keep going on forever. To get from 5 to 10, I add 5. 10 to 15, I add 5. Next one would be 20. You would add 5. It's a common difference. It's almost like slope, right? We have a constant rate of change. Now I could also go, I'm going to just do this off to the side. If I did 15, 10, 5, ... That's a sequence as well, but now you're going down 5. This plus 5 or this minus 5, and this is what we call a common difference. And all arithmetic sequences have a common difference. I'm going to go back over to the side here and look at say I have this, 2, 4, 8, 16, 32. There's definitely a pattern here, and this went back to the ones we were identifying slope. But this rate of change isn't constant. To go from 2 to 4, I add 2. 4 to 8, I add 4. There's a pattern here of doubling or multiplying by 2, but there is not a common difference. This is multiplication. In order to be a common difference, we have to have addition or subtraction. So there is surely a pattern here, but this is not an arithmetic sequence. This is what we call a geometric sequence, and we'll get into that. This is something that's exponential, where this is something that would be linear because we have a constant rate of change. here's what we're going to do. Write the next 3 terms of the arithmetic sequence. So just like in our slope ones, if it tells me it's an arithmetic sequence, you know that there's going to be a common difference. -12, 0, 12, 24. There's my next 3 terms. Hopefully you see, because this is an arithmetic sequence, you are going to have a common difference. And you can see, hopefully, this is going up by 12s. This would be 36, this would be 48, and this would be 60. So I don't need my comma there. So yeah, letter B. Again, it tells me it's an arithmetic sequence. I know there's going to be a common difference. I got to figure out what that is, and we just got to figure out, how do I get from 0.2 to 6? How do I get from 0.6 to 1? How do I get from 1 to 1.4? If there's a common difference, to me it's really easy to see, to go from 1 to 1.4, I'm adding 0.4. And that is exactly how I get from 0.2 to 0.6 and 0.6 to 1. So I'm adding 0.4. So this would be 1.8. This would be 2.2, and this would be 2.6. Again, your common difference in that first letter A, hopefully you can see that it is a positive 12. Your common difference in the second one, hopefully you can see that it is a positive 0.4. And remember, we can go in decreasing order as well, which means that common difference may be negative, but I have 4, 3 3/4, 3 1/2, 3 1/4, and then I am going to say, what are the next 3? And hopefully you can see that from go to 4 to 3 3/4, you are decreasing by 1/4. Here we are adding 0.4. Here it was a positive 12. Here it is decreasing. So I'm subtracting a fourth. A fourth less than 3 1/4 is 3. A fourth less than 3 is 2 3/4. A fourth less than 2 3/4 is 2 1/2. Those are the next 3 terms in that sequence. We're going to make the connection with graphing some of these. We're not going to graph a ton of them, but I want us to be able to piece together why arithmetic sequences coincide or kind of go together, why it's good to do these following up linear equations. So this is going to be graphing an arithmetic sequence. And here's my sequence: 4, 8, 12, and 16. It tells me it's an arithmetic sequence. You can see that it's increasing. Hopefully you see that it is increasing by 4s. And we're going to graph that. The way that we graph these sequences is we use the position that it's in. This is in the first position. This is in the second. That's in the third and the fourth. And we are going to treat this just like ordered pairs. Just like ordered pairs. Our position, or our n, the number of the position, what position it's in, is going to be thought of as kind of like our x. And the term, what's produced on the back side of that, or our a sub n, is this number. So I have 4 positions, and these numbers correspond with it. And hopefully you would be able to tell me that if this is X and this is Y, you have a constant rate of change, a common difference. It's going to look linear, but we're not going to graph it as a line because it's actually not a line, it's just data points. So I'm going to make a little first quadrant coordinate plane here because those are all positive. Here's my Y, here's my X. I'm going to go by 2s. 2, 4, 6, 8, 10, 12, 14, 16, and it doesn't have to be exact here, but I just want to show you how, when I plot these, they do indeed have that correlation, that positive correlation. As X is increasing, Y is increasing. As my position increases, my term number increases. And more specifically, it increases by 4. Very similar to slope, yes? So 1, 4, right there. 2, 8, right there. 3, 12, right there. 4, 16, right there. And you can see that these I can't connect those dots because it's not a line, it's not a linear equation, but they do have positive correlation and are definitely somewhat linear. So here's how we use this, because we always want to model, just like we did with our lines of fit. We got a line of fit that represented the data, because then I could extrapolate. I could pick out, well, hey, Mr. DeLong, this is nice, this is a sequence here, but what about, what's the value of something that's in the 150th place? Do you certainly want to go from 4 up by 4s out to 150 to get that? You do not. And that's what it's going to be able to do. We're going to be able to write equations of these sequences to predict any number in this sequence in any position. Or if I know the number, I could find the position. Just like we did with an equation. If I plugged in an X, I got out a Y. If I knew Y, I could certainly find X. And that's the idea behind what we are doing. Here's another. First quadrant. I'm not even going to label this one. I'm just going to say this is 115. I'm going to make some dots that sure look like it's in a sequence. It sure looks like the correlation, the model would be a negative slope, a negative common difference because it's falling. But I'm going to write this out. I've got 115, 212, 39, 46. Question is it an arithmetic sequence? And in order to be an arithmetic sequence, you got to have a common difference. And I can see if I go from 15 to 12, I'm going down 3, 12 to 9, 3, 9 to 6, 3. So it's certainly a sequence, and you have 15 is in the first position, 12, 9, 6. I have that. Your common difference is -3. So we want to be able to look and tell. How do you tell if it's arithmetic? If it has a common difference. How do we use this? And you're going to do a ton more of this in Algebra 2. We are going to introduce this today, and we're going to do some problems with it, but not a ton. This is your equation for an arithmetic sequence. a sub n is equal to a sub 1 plus n subtract 1 times d. We've got to label some of these. Remember from the first page, this a sub n is the nth term. Whatever term I decide it to be, which one do I want to find of an arithmetic sequence? This a sub 1, that's the first term. That's your first term in your sequence. Then to that first term, we are going to add the n, which is the number of terms. We're going to leave that for now, times the common difference. That's your formula. Nth term, first term, common difference. Here's how we use it. We are going to write an equation for the nth term of the arithmetic sequence. So it's telling me it's an arithmetic sequence, which is good because I know that it's going to have a d or a common difference. I'll say 14, 11, 8, 5, and we'll just say this continues on with that pattern all the way out. Then find a sub 50, meaning I want to find the 50th term. And I certainly do not want to keep subtracting 3 from here. Remember, term 1, 2, 3, 4, 5, 6, 7, all the way out to 50. Subtracting 3 each time is going to give you the wrong answer if I make one little mistake subtracting it out. And we don't want to do this. We want to come up with a general formula that I can use for this sequence so I can find the value of any term, whether it's the 50th or 150th. You use this formula. A sub n is equal to a sub 1, which term I'm looking for, times the first term, plus the number of terms minus 1 times d. Let's plug in what we know. A sub n, my general formula is going to be my first term, 14 plus n minus 1 times my d, which is my common difference. D in this case is going to equal negative 3, so I want to multiply that by negative 3. Now I just need to simplify that, and I will have a general formula. I'm going to need to distribute. A sub n is equal to 14 plus negative 3 times n, negative 3n, negative 3 times negative 1 plus 3. Got a couple like terms to combine here, and I'm definitely going to write this so it kind of models a linear equation, meaning my variable is going to come first. Negative 3n plus 17. Once I have that, the general formula from it, just like we made a formula for the line of best fit, because that allowed me to tell what was way out to the right on the x-axis. I could choose any value of x, plug it in, and find my y. That's what we're doing here. I can find any term. In this case, we're going to find the 50th term, but I could also find the 150th term, the 250th term. So here's what we do. There's my n right there. The 50th term, or a sub 50, is going to equal negative 3 times that 50 plus 17. A sub 50, or the 50th term, is going to equal a negative 150 plus 17. The 50th term then would equal negative 150 plus negative 150 plus 17, negative 133, and that's what I got. Always with these, because of this distribution here, watch your negatives. See if this answer makes sense. It does to me, somewhat, hopefully it is, because it's negative. And if I'm going down by threes, it makes sense that somewhere way out here in the 50th spot, it would be a very small number. It's going to be negative. That negative 133 makes sense. If this came out to a positive 133, or let's say you had missed this negative here and had it 167, that certainly wouldn't make sense that I'm going up to 167. If I'm starting 14 and going down by threes, 167 out here ain't going to make a lot of sense. We find the formula that we can use to find any term based on the values that are given.